I want you to picture the inside of a high-speed automotive pump or maybe an aerospace fuel line. To us, it just looks like metal piping. But if you shrink down to the microscopic level, it is an absolute war zone.
It really is.
We're looking at a new study out this month, January 2026, that explores what happens when you take cutting-edge 3D printed metal and, well, throw it into that chaos.
Yeah, this is a study led by Maria Beatrice Abrami and her team. They were trying to solve a very real, very expensive problem.
Which is?
You see, these 3D printed aluminum parts are fantastic. They're lightweight. You can make complex shapes, but fluids absolutely chew them up.
And we aren't talking about something simple like rust, right?
Yeah.
This is pure mechanical violence.
Exactly. It's called cavitation erosion.
Right. So when a pump spins fast enough, the pressure in the fluid drops.
And it drops so low, it basically rips the water apart into tiny vapor bubbles.
But then those bubbles hit a high-pressure zone and they just implode.
And that implosion creates what they call a microjet. It's a tiny stream of fluid moving at incredible speeds. It hits the metal surface like a hammer.
A tiny hammer that strikes thousands of times a second. Eventually, the metal just gives up, it fatigues, and chunks start flying off.
So the team's mission was pretty simple. Build a shield. They took a standard 3D printing alloy, AlSi10Mg, and tested 3 strategies to see what survives 8 hours of this ultrasonic torture.
Okay, so what were the contenders?
Pretty standard stuff, really. First, you have the bare aluminum alloy.
The control group.
Right. Second, a single coating of electroless nickel phosphorus, or NiP. It's known for being quite hard and tough.
Okay.
And third, what they called a multilayer system, that same NiP coating, but with a top layer of hydrogenated amorphous carbon.
Diamond-like carbon, or DLC.
That's the one.
So bare metal, hard coating, and the sandwich. Now, I have to say, I looked at the data for that single NiP coating, and I honestly thought I was misreading the chart.
I'm not surprised. You expect a protective coating to, well, protect. But the single NiP coating was a catastrophe. In terms of mass loss, it performed significantly worse than the bare aluminum.
Worse? So wait, adding armor actually made the part weaker?
It accelerated the destruction. The problem is, NiP is hard, but it's also quite brittle. So when those cavitation shockwaves started hammering it, it shattered.
It just broke apart.
It detached in these large, hard fragments.
I think I see where this is going. Because this is a closed system. Those hard fragments, they don't just disappear.
Not at all. They stay in the water. They turn the water into a slurry.
So those shards acted like shrapnel, just swirling around and blasting the softer aluminum underneath.
You got it.
That's horrifying. It basically turned the fluid into liquid sandpaper. The data showed it only protected the surface for, what, about 6 minutes?
Roughly 6 minutes, yes. The bare metal lasted 5.
So you get 60 seconds of safety before the coating turns into a weapon against its own part.
That's a good way to put it.
Okay, so here's my question. If the nickel coating failed because it was too brittle, why on earth would the sandwich work? I mean, you're just putting diamond-like carbon, which is even harder and more brittle, on top of that same failed layer.
Right. It seems counterintuitive.
Shouldn't that just create more shrapnel?
That's the logical thought. But this is where material science gets really interesting. It's all about synergy. The multi-layer system didn't fail in 6 minutes. It lasted 228 minutes.
Wow. From 6 minutes to nearly 4 hours. That is a massive difference. So why?
It worked because of the layering. DLC is incredibly hard, so it can take that surface punishment. But it's very, very thin. If you put it directly on soft aluminum, it's like putting an eggshell on a soft pillow.
If you punch it, the pillow just deforms and the shell cracks.
Exactly. But the NiP layer underneath acts like a firm mattress. It provides the load-bearing support.
So the mattress keeps the eggshell from flexing and cracking.
That's it. The NiP supports the DLC, and the DLC protects the NiP from the initial hits. They cover each other's weaknesses. The total mass loss went from 123 milligrams with the single coating down to just 44.
Still, nothing is invincible. The study did note that even the winner eventually failed, and I found the where it failed really interesting.
At the morphological discontinuities?
Which is a very fancy way of saying surface defects, right?
Yep, rust spots.
And that brings us back to the fact that this is 3D printed. We're talking laser powder bed fusion. If the laser leaves a rough patch or some unmelted powder,
you get a defect. And you can't just coat your way out of a bad surface finish. The coating didn't stick as well to those rough spots, and that's where the water eventually worked its way in and peeled everything off.
So the big takeaway here isn't just use harder materials. It's that hardness without structural support can actually be a liability. You need that sandwich effect.
And you have to look at the whole system. If your protective measure fails in a way that creates debris, you might be designing something that destroys itself faster than if you had done nothing at all.
It really makes you wonder about other industries. I mean, how many safety layers are out there right now that are just one stress test away from turning into shrapnel?
Definitely something to chew on. Thanks for joining us on this deep dive.